As it happens, the Scala API has a type in it for doing these sequences when they are mutable, and that type is called buffer. Okay, so instead of implementing our own interface, we could implement buffer. So what would we have to do in order to do that? So here's the API page for Scala collection mutable buffer, and there are actually a number of subtypes of this, one of which is a list buffer. There's also the array buffer. The array buffer is a mutable sequence that's based on arrays. The list buffer is a mutable sequence that is based upon a linked list. Now, it's not the type of linked list we're going to write first. It's more similar to the one we're going to write second. But the set of methods that we have to write is the same either way. So we are using inheritance here. There are a set of abstract methods that we have to implement if we want to make a subtype of buffer. They are plus equals colon, so this is an append, this is a prepend, the apply method to index, clear, insert all, iterator, length, remove, and update. So whereas the interface that we came up with just had apply, update, and insert instead of an insert all and a remove, this has added a few additional methods onto it. And I would like to have us implement this, make a subtype of this. And one of the nice things about making a subtype of this is that if we implement these 10 methods, we get all of these other methods somewhat for free. We'll see there's a proviso to that. We actually have to do a little bit more work to make them all work the way that we would want to. But for a small cost, we can get a lot of things. So I'm going to go ahead. I'm going to try to do a copy on all of those because I don't want to have to retype all of them. And then I'm going to go ahead and in our linked list package, I'm going to make a new class that I will call, how about mutable SL list. So mutable singly linked list, because we're also going to write one that uses a doubly linked list. And this will take a type parameter A, and it will extend mutable.buffer of A. So we'll put in an import of collection.mutable. And of course this says that it needs to be abstract because there are 9 unimplemented methods. So I'll copy and paste these into here. I can get rid of the descriptions. Okay. We don't need the abstract either. Okay, one more. There we go. The type, instead of being buffer this type, is mutable SL list .this .type, because it has to be the type of the current class that we are in. It turns out that you can just let it infer the type. We could just put an equal sign and it would figure it out, and that would work, but I'm going to go with being explicit. And to make this happy so it compiles, there we go. Okay. This is a linked list. When we write a linked list, we have to create our node class. And no one else needs to know about our node, so it'll be private. It is going to be a class. This is a mutable linked list, so it cannot be a case class. I will call it node, and in fact it is mutable, so I'm going to make everything inside of it vars. So I have the data again, which is of type A, and I have the next, which is a reference to another node. That's exactly what it looked like in our previous singly linked list. What about data? Well, for our previous singly linked list, we only kept one element of data, and that was the head, which was of type node, and it started off as null. Now, turns out I can't use the variable name head here, and if we hover over, var, even with that, I really can't use the name head because buffer has a head in it. All of the standard collections in Scala have a method called head that we could go find here in the API, and I can't give a method the same name as that. So instead, I'm going to call this one HD, and I'm also going to create a tail here. And the reason I'm going to create a tail is because one of these methods that's inside of buffer is an append. It adds to the end. If I don't keep a tail, in order to add to the end, I have to walk all the way through the entire list and add it there. By keeping a tail, I can make it so this is an efficient operation. It'll happen in order one time. And so if you build up a linked list with using plus equals, that will be an efficient thing to do, as long as we keep track of a tail. If I don't keep track of a tail, it will be a very inefficient way to do things. But you will also see that having a tail adds some certain cost to it. And I can't call it tail because, once again, that's also part of the standard collections. So I'm just going to call it TL. Okay. Now we need to start implementing methods. Where are we going to start? You know what? I'm actually going to introduce a third variable because I'm looking around, okay, what would be the easiest thing to write? By the way, that's how I always write these things. I'm like, what would be easiest? And it's, I joke, part of the reason I do it is to give myself a sense of completion. And I recommend you do that too. You know, if you have implemented these methods and you feel like they work, that's good. But there's another reason to write the easy stuff first, and that is because by writing the easy stuff, you might help yourself to better understand what's going on so that when you get to the harder stuff, it's not as hard as it would have been if you had started there. So length looks like a fairly easy one to me. It turns out I could write this with a for loop, or actually it'd be a while loop, that goes through and keeps going as long, walks through the list and counts all the elements. But that would be an order in length. I can make this an order 1 length if I add another private var. I'm going to call it num elements, and it starts off at 0. So we don't have any elements, and length just returns that. In fact, let's go ahead and let's put some carriage returns in here. So that means we won't be able to see all of these methods in the video. Okay. What's the next easiest? Actually, clear is pretty darn easy too. So when I clear this out, I'm basically setting it back to the state it starts at. So the head goes back to null, the tail goes back to null, and num elements is set to be 0. Okay. Next up. Well, it turns out that the apply and the update methods can be written pretty much the exact same way that we wrote them for our singly linked list. When we do an apply, first I'm going to require 2 things. Now I didn't do this previously. Previously I just said I'm going to require that the index is greater than or equal to 0. But here I'm also going to say that it has to be less than num elements because I have a length for my collection. Well, at this point I can say var rover equals the HD variable for I in 1 to n. Actually, let's 0. No, 1 to n works. 1. Yeah. I could also do 0 until n. That would actually, then I'd be counting on the indices. Here. Rover equals rover dot next. So every time we move it forward to the next element, and then at the end we have to give back the data that's stored in that node. Okay. Fairly simple, very much like what we had before. We can real quickly copy this. In fact, let's copy that part there, because update looks very, very similar. It's going to run through, but instead of giving back the data, it sets it equal to new elem and overwrites whatever value had been there. So we've written now 4 of the methods. We have a length, we have a clear, we have an apply, we have an update. We'll come back in the next video and we'll decide what to do next. What thing will be the next easiest for us to do on this particular list.